Hello and welcome to the presentation of this work. I will explain to you the experimental setup that we used to perform a real-time hybrid substructuring test of a prosthetic foot. There are about 50,000 amputations of the foot per year in Germany. Prosthetics are used to help the patients to regain their independence in everyday life and to mimic the function and the feel of the lost body part. However, it is challenging because the functions of, for example, the foot are manifold. We want our foot to help us balancing, absorb ground impact, but also to propel us forward as efficiently as possible. Because prosthetics are not yet able to mimic all these functions, we can observe an altered gait pattern of amputees compared to able-bodied people. So to improve prosthetics further, it is important to understand the dynamic interplay between the human and the prosthetic foot. This means that the prosthesis developers have to understand how a human adapts their gait pattern depending on the properties of the prosthetic foot. Our idea to investigate this dynamic interplay is to use real-time hybrid substructuring. RTHS is a method to analyze the dynamics of a system, and this is done by splitting it into a numerically simulated part and an experimentally tested part. Because we want to know how the dynamical system behaves as a coupled system, we need to exchange some information between them, we need to couple them, and this is done by exchanging displacement and force information. And as the name real-time hybrid substructuring infers, this data exchange is done in real time. So when RTHS is applied to test prosthetic feet, the dynamical system we want to analyze is the amputee wearing the prosthesis. The amputee is modeled in our case, and the prosthetic foot is tested experimentally. The advantage of this setup is that we can analyze the dynamic interplay between the amputee and the prosthesis without bothering a testee. The research question that we pursue in this work is whether it is possible to perform such an RTHS test. For this purpose, we propose the following setup. It consists, as in any RTHS test, of a numerical part, a transfer system, and an experimental part. In our numerical part, we have the modeled amputee, which will be a two-dimensional model for this first proof of concept. The transfer system is responsible to transfer the force and the displacement information between the numerically simulated part and the experimentally tested part. So we need an actuator, which is in our case a steer platform. We need a force-torque sensor to measure forces and a torque. And we need a digital signal processor, which is a D-space system in our case. And the experimental part is obviously formed by the prosthetic foot in our case, which is an ESAR foot, stands for energy storage and return. And the specific model number is 1C40. It is a foot by Otto Bock, and to be specific, it is also a right foot. The numerical time integration scheme works with a sample time of 0.2 milliseconds. And the data exchange and the control are done at a sampling time of 1 millisecond. One important research question is how human gait can be modeled. The question arises, how do humans walk? And you would probably not be able to tell me what your objective is when you walk. And this is also a research question that bothers biomechanists. The only thing that we can do is we can observe humans in gait laboratories. And so human gait is a periodic motion where we perform a stride after stride. And in each stride, which we can also call gait cycle, the leg performs a stance phase and a swing phase. So there are several models in the literature of biomechanists, and the requirements for our model used in the RTHS test are that it is real-time applicable, that it represents basic human gait characteristics. Then we want to put the focus on the stance phase. So this is the phase where the gait pattern of amputees significantly alters from the gait pattern of able-bodied people because of shorter stance times on a prosthetic leg and so on. And in this first study, we want to have a model that is as simple as possible. So if we look into the literature of biomechanics, one can find the so-called spring-loaded inverted pendulum model, which is also called slip model. In this model, the whole body mass is concentrated in a point mass, and the legs are represented as massless springs. This is a passive model, meaning that if we give it an initial push with an initial velocity and at an initial height, the model walks on itself passively. However, this model is not robust and it falls when there are slight disturbances. So we selected the next more complex model for our study, which is the so-called virtual pivot point model. Compared to the slip model, you see that we have an added trunk, and this model implements the so-called virtual pendulum principle. The virtual pendulum is a point observed in humans and also some animals, like for example chicken. And in this point, the ground reaction forces intersect. The ground reaction forces are the forces that the ground exerts on the human body. And the virtual pivot point is at the point above the center of mass. It is supposed that this virtual pendulum principle stabilizes the trunk and therefore human walking. In the VPP model, this virtual pendulum principle is implemented by using an additional hip torque, which is here denoted with tau VPP. With our model, we want to model an amputee, so we need to amputate one leg. In our case, this is the right leg, and we cut it at the ankle joint. For the RTHS setup, we need to know the location of this interface position. This is the endpoint of the amputated leg in the VPP model. The question is how we can determine this location. So the force in the remaining leg and the force in the prosthetic foot need to be in equilibrium. In order to determine from this setup where the interface location is, we will need to know the stiffness of the prosthetic foot. This is, however, in general not known, and in particular, it might also be nonlinear stiffness characteristics. So our idea was to implement a mass as an additional degree of freedom, which we can solve for. And this mass has a very small value such that the dynamics are only barely modified. And since this mass leads to a high frequency vibration, we need to damp the oscillation, and this is done by inserting an additional damper in parallel to the leg spring. Here I want to show the results of a test. We performed one gait cycle where the model starts on the left leg, and then it performs one stride, meaning that the right foot will overtake the body weight, the left leg swings forward, touches down, and the gait cycle stops when the model is in the same position as it is here. Let's see the results. First in real time. And as this might have been a bit quick, I have a slowed down version as well. You might see that the video of the steer platforms of our experimental test is upside down. This is for better visualization. So for now, we could be happy and say the test worked. For sure, it is important also to see whether tests replicated human gait characteristics. So let's look at them. One gait characteristic is the center of mass motion. In humans, we can observe a sinusoidal shape of the center of mass motion with a magnitude of about 4 centimeters. In our RTHS experiment, the overall shape looks similar. However, we can see an increase of the magnitude here in the late stance phase of the right leg. This is because we do not have a rotational degree of freedom at the ankle. So the hip and also the center of mass need to lift when the whole body rotates around the foot, and in particular when it rotates around the toes. Another important gait characteristic are the ground reaction forces. In y direction, they should exhibit an M-shaped profile, and in x direction, they should be point symmetrical with decelerating forces as long as the feet are, as long as the foot is in front of the center of mass, and we should experience accelerating forces when the body is in front of our feet. And the black dashed line here represents the body weight. In our RTHS experiment, the results look as is shown here. So the overall force profile look pretty similar. However, the minimum between the force humps in y direction is very low, and we can see a steep initial rise of the force in the second portion here. Furthermore, we looked at the angle of the trunk and the forward velocity. And from here, we can see that the upper body rotates backwards and that the model loses velocity. In periodic motion, we would rather expect an oscillating motion around 0 degrees here. There are several reasons why our model loses energy, but the major reason lies in the actuator performance of our steer platform. So what we can see here is the desired lag velocity of one steer platform's lag and what is really executed, and that there are large discrepancies between them. In this video, I show you how the experiment looks like, and this steer platform lag on the left is the lag that is shown here in the figure. And again, in a slowed down motion, this is how it looks like in the RTHS test. Alright, to bring all this together, I want to show you an animation of the model. With the results that I've shown, you might now see that the model rotates backwards during the step and that the hip is lifted extensively because of the stiff ankle joint at the end of the right stance phase. But all in all, it looks quite promising, which leads me already to the conclusion that we could show that an RTHS test with a prosthetic foot is in general feasible, and that the gait characteristics according to the VPP model could be replicated. So we can conclude that RTHS may be a suitable test method that may help to understand the dynamic interplay between amputees and prosthesis and will therefore help to improve prosthesis further. Still, there are plenty of research questions until we can use this kind of testing method in the development phase. For example, we have to tune the model parameters of the amputee such that it can perform multiple steps. We should improve the actuator and add, for example, an actuation to our ground to have a larger workspace. We should also investigate whether changes in the prosthetic foot change the gait characteristics, and should also consider using more complex gait models. This is the list of the used references. And we thank you very much for listening and hope for an exciting discussion at the conference. If you already now have questions or later on, please do not hesitate to reach out to us. Thank you.